Okay, I believe we're live. I'm getting pretty good at doing this pretty snappy, so again, let me just check, make sure, because you don't want to record the entire thing and then find out that, like, there was no audio or something. That would really suck. So, let's just make sure everything is good. Yep, everything seems good. Okay, welcome back, everyone. Let me just minimize this. Okay, quick review and intro and whatnot. We're going through the NNFS Neural Networks from Scratch book, written by, I don't know how to pronounce his name, but he's a YouTuber, and I forgot his actual name, and I don't know how to pronounce his channel's name, but anyway, it's Neural Networks from Scratch in Python. We're going through it, but as you can see, we're doing it in Golang, which is pretty interesting. So first things first, link to the book. This is the book over here on the left side of my screen. Link to the book is in the description. You could also go to nnfs.io to buy a copy, either an ebook copy for $30 or paperback or hardcover for whatever they cost. Excellent, excellent book. I remember when it came out. Not sponsored by them, but highly recommend. And especially if you want to follow along with this and you want to have a copy of your own book. But I'm going to be going through the book. I'll be skipping some paragraphs here and there because there's no need for me to read the paragraph and also explain things. What else? Any other crucial pieces of information? No, I don't think so. Okay, so let's talk about what we've been doing so far. So far we've talked about what tensors are. We've talked about what arrays are. We've talked about a basic structure of a neural network and how they work. All of that is in previous videos. There's a link to the playlist, I believe, in the description. Let me just make sure. Yeah, there's a link to the playlist in the description. Go check that out if you haven't already. In this video, as the title says, we're going to talk about batches, specifically batches of data. So how do I get the chat back? I want the chat back. Give me the chat back. Thank you. We're going to be talking about batches of data. So until now, we've been using one sample. So here are our inputs, and the inputs is a one-dimensional vector, I guess you would call it, using the syntax, the words that we uncovered in the last video. Go check that out, because in the last video we talked about tensors, arrays, matrices, vectors, words that are often used in machine learning that people don't really know what they mean. Give me a second, I'm going to close the door. Sorry about that. Okay, so we talked about what tensors are, we talked about why they're used in machine learning, and arrays and stuff like that. So anyway, until now we've been using a vector for our inputs, just one sample. Oh boy. And we have this, we have these weights which are modeling how many neurons? 1, 2, 3 neurons. Again, check the previous videos to understand why we have this many inputs and why this amount of weights corresponds to this amount of inputs for 3 neurons. And then we have 3 biases here, each one corresponding to a neuron, and this is just a vector. And we're doing the dot product here. This is just this right here is just a forward pass through a layer. And all of this is just like raw coded right now. We're going to turn this into object-oriented stuff later. Forward pass. But anyway, so today we're gonna start making the inputs look a little bit more like the weights. We're gonna have a two-dimensional thing of inputs. We're gonna have a bunch of inputs. We're gonna have a batch of inputs that we pass into the neural network all at once. Okay, so let's talk about that. So to train neural networks, we usually train them with batches. So until now we've had inputs. He's had inputs looking like this in Python. We've had it looking like this. The data is simply a vector. The shape is just a 4. Because there are just 4 elements. It's not like a 2D thing. It's just a 1D array or a vector. Same words. But most of the time, a neural network expects many samples for 2 reasons. A, it's faster, as he says, because you could parallel process things. And B, imagine trying to train a neural network to fit to 1 sample, and it fits to that sample really well. Okay, moving on. Then it tries to train to another sample, and it fits to that sample really well. Okay, moving on. Then it tries to train to a new sample, and it trains to that sample very well. It's kind of going to forget the first sample. It's going to like train to each one of them very well, but the first 2 it's going to like forget about and focus on one of them. By training with a random set of all your samples, you get the AI to generalize, to learn to generalize things. So to do this, to visualize this, there's actually an animation. I spoke to the author of the book. He says that it's okay to use the animations as long as I say where I'm getting them from. It's pretty clear where I'm getting them from. You go to nnfs.io, you buy the book, and you have access to the animations. So let's check out, oh boy, I don't want that. I wanted a new tab. So let's check out this animation to visualize exactly why, and this is his YouTube channel, link to his YouTube channel is in the description, why exactly we train with batches. So when you train with a batch size of 1, which is 1 data point, and you keep on training with just a batch size of 1, you see how the line is moving around a lot and it's jittering, and it doesn't really remember any previous samples, it's just sort of flying around. And in the end, as you will see, here, let's speed this up a little bit. In the end, here you have the samples over here, and you see how this line is jumping around because it's kind of forgetting all the other ones, and it's just flailing, and it's not really doing a very good job. So let's just watch this, and as you can see, it's having a hard time fitting to the data in a nice way, whereas you and I probably would be able to just draw a nice line. It kind of didn't fit to the data very well, did it? It was too much to the last sample that it saw. This is a batch size of 4, and this one's going to be a little bit better. Speed this up. And you see it's flailing around a little bit less. It's still flailing quite a bit, and you see that it is fitting to the data in a better way. It's better than it was before, right? But now let's just see a batch size of 16, and when you get to numbers like this, 16, 32, you see how the line is really starting to focus and narrow in. This is called generalization. This is a really good fit. And then finally, I think 32. 32 is a really nice batch size. And you see how the line is steadily getting into its place, and then it sort of hovers in that area, and boom. And you see how the 32 was even faster, not just because we increased the speed. So there you go. There's a nice visualization as to why we use batches in machine learning. So this is what a batch would look like. The input data would be in a form of a batch, and in this particular case, he has a 8x4 situation. This is one sample of data, this is another sample of data, this is another sample of data, this is another sample of data, and this is a 2D array or matrix. And yeah, so he has this in a two-dimensional list. In Python, we're going to have this in a two-dimensional slice. Actually, it's probably going to end up being just a one-dimensional slice, like the raw weights, and then we'll pass that into our tensor library that we're using. By the way, we are still in chapter 2. In terms of our directories, we are still in chapter 2. Because chapter 2 is a big chapter, apparently. So, here we go. So his inputs are going to look something like this. It's a two-dimensional list for him. There are 1, 2, 3 inputs here. 3 sets of inputs, rather, and each set of inputs has 4 parameters, I guess you would call it, arguments. I don't know. You could also call it a feature set. There are a bunch of samples. These are just words, or observations is another thing you could call them. And he has it put into a matrix. And now that they are in the situation of a matrix, remember before we were doing the dot product on our weights and our inputs. Now that they're in a matrix, we need to talk about matrix multiplication, or to get the matrix product. How are we going to get the matrix product? How are we going to go through this and get the output properly in a nice way? So that's exactly what we'll talk about. The matrix product is an operation in which we have 2 matrices, and we are performing dot products of all the combinations of rows from the first matrix and the columns of the second matrix, resulting in a matrix of these 2 atomic dot products. So the matrix multiplication is essentially, you take a look at, visualizing how a single element in the resulting matrix from matrix product is calculated. See animation for the full calculation of each element. This is looking a little bit, strange. I guess, which one is the weights and which one is the inputs? And which one is the output? I think this is the output, right? Yeah. So it's going to be this row with this column, 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 and that's how you get these values. And then we're going to have this row with this column, which will get you this value. So remember, the dot product was between two vectors, between 2 arrays. The dot product looked like, here, let's just do a quick review. You should really go and watch the last video to remember what a dot product is, but imagine we had x equals, let's just do int 32, 1, 2, 3, and then we have, actually let's call this A, and this one is called B. And this is not a correct Golang syntax because I'm just plowing through this. Actually, this is correct Golang syntax. And then we would have C colon equals So C would be the result of, C would be the dot product, which is A index 0 times B index 0 plus A index 1 times B index 1, etc., etc., as far as we go. As far as A and B are, that's what the dot product is. It's the first element of each one. It's the product of the first element of each vector plus the product of the second element of each vector. And so over here, what we're doing is we're going through the weights, and we're using this as the first set of weights for the first neuron, and we're doing the dot product with this, and then we're using this as the second set of weights for the second neuron, and we're doing the dot product between these two and this, and then we're getting all our outputs, and we get 3 outputs. So now that we have many inputs, and this is 1 input, this is 2 inputs, this is 3 inputs, this is 4 inputs, 4 sets of inputs, we have to get the dot product of each one of these. And so when we get, I feel like there's a lot more in this thing than there should be. There are only 1, 2, 3, 4, 5 neurons, and each neuron should be giving over. Let's take a look at the animation. Nope, I made the mistake again. Let's take a look at the animation, because I'm forgetting this. Okay, so we have AB, which is a matrix, and then we, A is this matrix, and B is this matrix. I guess these are the inputs, these are the weights, potentially. Not sure. So the first value is going to be the dot product of these two. Right? So you see how it's taking the dot product of these two things. And then the second, so that's going to be over here. Then the second value is going to be the dot product of these two things. Right. So notice how it's rows and columns, which is interesting, because until now we might have visualized it as rows and rows, but this is rows and columns, and it's taking the dot product of each of these and bringing it in, as you can see. And that's how it populates this entire new two-dimensional array. Okay. So what does this represent in terms of like weights, inputs, bias, output? Like what is this? This is, not sure. I'm actually not sure what this would represent. Because I was expecting it to look like, right, here are the outputs. I guess this is just an example of a matrix multiplication. This is just matrix multiplication, and now so now he's going to explain it. A equals this, and this is that, so A times B equals, is supposed to be an equal sign for some reason, it's faded, 1 times 2 plus 2 times 3 plus 3 times 4, which is 20. Right? Yeah. In other words, row and column vectors are matrices with one of their dimensions being a size of 1, and we perform the matrix product on them instead of the dot product, which results in a matrix containing a single value. In this case, we perform a matrix multiplication of matrices with shape 1, 3, and 3 and 1. Then the resulting array has a shape of 1, 1, or a size of 1. So notice how, in order to perform a matrix multiplication, you need to have as many values in this one's row as there are in this one's column, because this guy's being paired up with this guy's being paired up with this guy, and this guy's being paired up with this guy. Hey Keeves, my older brother's in the chat. Nice to see you too, man. Sorry if you're not here anymore. I didn't see your message. So this guy's being paired with this guy's being paired with this guy, this guy's being paired with this one. So this one has a shape of 1, 3, and this one has a shape of 3, 1. So they need to have, this one needs to have the same amount in its row as this one has in its column. Another way to say that is this one needs to have the same amount in its second shape value, the second shape value is 3, as this one has in its first shape value. And so this one is 3. So these two have to be the same, which is a nice trick to know. In order to do matrix multiplication, these two need to be the same, otherwise you're going to get an error. Furthermore, since these two values, the first row and the first column, are coming together to make one value, you actually end up with a vector with a shape of 1 by 1, which is just one value. So notice actually that the outside values are combined are the end shape that you will have. And we can check this with the larger thing that we have over here. 1, 2, 3, 4. Well, actually no. 1, 2, 3, 4. This one has 4 values in its row. 1, 2, 3, 4. This one has 4 values in its column, and these two are coming together to make this guy. And notice how this one's shape is 1, 2, 3, 4, 5. 5 by 1, 2, 3, 4. It's a 5 by 4. This one's shape is a, I guess, 4 by 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. This one's shape is a 4 by 5. So what would this one's shape be? Well, this one's shape would be a 5 by 5 because it's a combination of the outermost shape values. Okay. So now that we have a general idea of what the matrix product is and how to get the matrix product, let's bring this down into our exact situation. Transposition for the matrix product. So we're going to have to talk about transposition now. So how do we get suddenly from two vectors to row and column vectors? We use the relation of the dot product and matrix product, saying that a dot product of two vectors equals a matrix product of a row and column vector. The arrows above the letters signify that they are vectors. So the vector A times the vector B equals A times B. Sorry, the vector A dot vector B equals A times B transposed. We also have a temporary use for some simplification, not showing that column vector B is actually a transposed vector B. The proper equation matching the dot product of vectors AB, written as the matrix product, should look like this. So here we're taking two vectors and we're turning their dot product into like a matrix product situation. So to do that, we do AB. Right, the dot product of these two things, I guess this is the notation for a matrix product. The dot product of two vectors equals the matrix product of the first vector as a matrix, basically, times the second vector transposed. What does transposing mean? Transposed basically means, well, here, he's going to explain it. Here we introduce one more new operation, transposition. Transposition simply modifies a matrix in a way that its rows become columns and columns become rows. So here was your original matrix. This matrix transposed equals, so this row becomes its column, this row becomes this one's column, this row becomes this one's column, and this row becomes that column. And so you see how it just sort of rotates. You could almost envision, well, not actually, no, don't envision it as rotating. Simply the row becomes the column, row becomes column, row becomes column. Okay. And here we have another example of array transposition. Now we need to get back to row and column vector definitions and update them with what we have just learned. A row vector is a matrix whose first dimension size, the number of rows, equals 1. That's how you could think of a vector. A vector is basically a matrix with only one row. And the second dimension size, the number of columns, equals n, the vector size. In other words, it's a 1 by n array, or an array of shape 1, n. With numpy and with 3 values, we would define it as this. So this is an example of a vector. And we're not going to copy this into Golang yet because it's not important yet. But basically, he has a vector or a one-dimensional array with the values actually no, this is a two-dimensional. This is in theory a two-dimensional array because it has two shape sizes, but the first one is just a 1. So you can envision a vector sort of as a one-dimensional matrix, which I've said before. Note the use of double brackets here, right? He's using the double brackets to transform the list or the vector into a matrix containing a single row, and you have to perform an equivalent operation for turning a vector into a row vector. We can put it into a list and create a numpy array. So this is the list, and they're making a numpy array, and there you go. Now you have an array, a two-dimensional array where the first dimension is simply 1, just 1, because there's only one row. Again, note that we encase A in brackets before converting it to an array in this case, or we can turn it into a 1D array and expand the dimensions using one of NumPy's abilities. So NumPy has an ability to basically just expand the dimensions. I think that we probably have that in our tensor package as well. I haven't used it yet, but it's probably there. In fact, let's even see. So here, if we comment this out and we just fmt.println inputs, you see that we have a, oh, no, hold on. We have to cd into CHP2, I believe. Yeah, and then go run that. And so inputs, I don't like how it's printing it out, but anyway, inputs is a one-dimensional vector essentially. We could do, fmt dot println t dot expand, I don't know, function. I don't know, what does this do? I'm assuming this is the expand thing. Here, we could check the documentation. Golang Tensor. Nope, I don't want TensorFlow, I just want Tensor. And we can find that function and we can find out what it does. This is how you learn how to use a package. exp. No. 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 Yep. This is the one that we're trying to use. What do you do? Any documentation at all, please? Please? I don't think so. I wonder if it's built into the. I wonder if it's built into the type. Inputs dot. No, dot. I guess no, this is. Nope, 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 nope. Dims. That gives you the things. Yeah, they don't really. Yeah, they don't really let you modify it just by itself. There's a lot of stuff though. Not sure how we would do that, but if we need to do it at any point, we will look into it and we can figure it out, I'm sure. Anyway, moving on. Yeah, moving on. Where np.expand dims adds a new dimension to the index of access, a column vector is okay, so here we go. So that was the example of a 1D array, a one row vector. A column vector is like kind of the opposite, where the second dimension size equals 1. In other words, it's an array of shape n comma 1. It's like the opposite of what we were just talking about. With NumPy, it can be created the same way as a row vector, but needs to be additionally transposed. Transposition turns rows into columns and columns into rows. So this is the transposition operation. This one I know for sure we could do in our tensor package because it was kind of important. And let's show this. fmt.println inputs dot, is it just, yeah, dot transpose. And I think that this should just give you the transpositioned thing. Nope. Nope. Oh, yeah, okay, I guess it does it in place, which is pretty cool. So inputs dot transpose, and you don't even have to set this to a new thing. You simply print out inputs now, and it should be transposed. So let's print the compare and contrast. fmt.println inputs. Oh. Nope. Nope, that's weird. That's not how it should be. Maybe it's just a quirk. Inputs, comma, inputs dot shape. What is the new shape? 4. No. Okay, this is problematic. Oh, because this isn't yet. Yeah, I think the reason why it's having trouble is because this is not yet a two-dimensional thing. So let's try with. Hold on. We have to turn this into a two-dimensional thing because right now it's just a dense whatever. So t.with shape, and this should be 1, 4, I believe, right? Yeah, I believe so. Nope, something is still wrong. Transpose actually transposes the data. This is a generalized version of the in-place matrix transposition algorithm from Wikipedia. No, something is very wrong. What does this R mean? I don't even know what that means. I thought for sure that this would be super easy, and it should be, because we're using the function, but Yeah, the shape is still the same. It shouldn't be the same. It's the thing. How about just t dot transpose? And let's pass in inputs. And the axis should just be 0, I guess. And here we could say inputs equals and comma that. What's wrong? Cannot use a value of type as dense value. Why is this of type dense? This should be of type. This should be of type tensor. Maybe that's the problem that we've been having. Bar inputs, which is a type of t dot tensor, equals that. And now over here, hold on, let's comment this line out. Inputs dot. I wonder if t is just a shorthand for transpose. I think so. And it takes in an axis, which let's just say 0. Okay, let's try this. No. Okay, what if we change the axis to 1? No, same issue. There shouldn't really be an axis thing, should there even? Transpose. No, still same issue. Okay, let's try this. Okay, now there's an error. Right, okay. If error does not equal nil, fmt.println error. What's the problem here? Dimensions mismatched, expected 2 got 1. Transposing performance transformation of a tensor according to its axis. What does that even mean? Dimensions mismatched, expected 2 got 1. 4 comma 1, is that what it wants? Oh, this means that it's a column, I guess. Yeah, the R means that it's a row, and this means that it's a column. So it's not a very good visualization, but the point is, yeah, we got it at this point. Now this is a transposition. This right here is a transposition. This is a transposed version of our inputs. It's just a little bit annoying to visualize, but the C means that this is now a column, and you can see that the shape is 4 comma 1, as opposed to what it was before, which is 1 comma 4. I wonder if we could do inputs dot t, the axis will be 4 comma 1, and will this do it in place? Like, will this just modify the actual value? I wonder. Yeah, so that, okay, so there you go. So this is how we would do it. We would do inputs dot t, and this would modify the original thing, and that's a transposition. And you give it the new dimension situation that you want. I wonder what would happen if I do like 3 comma 1. It would probably just throw an error and not do anything. Yeah, it would, well, what? No, it did it properly. That's weird. Hold on. What if I don't pass anything in? Oh, okay. Apparently inputs.t just works no matter what. And why does it say that it's expecting an axis? Like as an argument. I don't know. Anyway, that works. So there you go. That's how you do transposition in Golang. Okay. So this is how it would look like with NumPy code. Import NumPy as NP. He has A and B. He's turning this in. He's turning these into matrices, one-dimensional matrices, and then he is transposing B, and he's doing the dot product, and then he's printing that out. Let's do the exact same thing as he's doing real quick. So let's comment this one out, and let's do this. So A : equals T dot new instead of doing it the way he's doing it, which he's just making actually no, let's do it the way he's doing it. So here, but we would have to do raw a colon equals int 32 1 comma 2 comma 3. And let's do the same thing over here, raw b. The reason why we have to call it raw a and raw b is because we have to keep our types like uniform in Golang as opposed to in Python, where you could just have an a equal a Python list and then also set a to be a NumPy array, which is blasphemous because you're just switching types around willy-nilly. 2, 3. I want to use the same values just so we get the same answer, 2, 3, and 4. And now let's turn these into tensor objects. So while he's doing it in arrays, we're turning them into tensor objects because that's the library that we're using. We're using tensor. I've called it T. And if you don't know how to install that library, check the previous video. So a colon equals t dot new, t dot with shape, and the a will have a shape of, I mean, now that I think about it, this is kind of funny, but it's going to have a shape of 1, 4. And t dot with backing, that's how you pass in like the raw values that you want to pass in. So raw a. So that's a, and this is going to be b. And b will start out with the same shape as a, just for now, just so we could use the example. So now a and b are both these same things, but we want that dot t. We want the transposed version of that. And so you see how these two lines actually look very similar, except this is how we do it in Golang. And then we want to fmt.println t dot dot a comma b. What's the problem? Cannot use b variable of type error as. Oh, sorry. Yeah, we would have to do b dot t like that, or we could do t dot transpose. Probably we could probably do this. No, forget it. We'll just do it. Yeah, we'll do it this way. B dot t. Because before, yeah, the dot t returns an error. Instead of modify, and it also modifies it in place. So we have to actually create t, and then we have to turn t into a transpose thing. Alternatively, we could just create t as a 4x1. We could do that, but we're not. So let's run this, and we get an error. Fascinating. Okay, why? Sorry. I'm doing a 1x4. It shouldn't be a 1x4. It should be a 1x3. That's my bad. Another error. Failed to perform dot, only handles floats, got int32 instead. Okay. Float 32. I can accommodate that. Float. Didn't realize that was a thing, but apparently it is. 20 comma nil. So it's returning the error of nothing, and this is the correct value. There we go. Correct. Excellent. And I think this is in the this returns a tensor. Yeah, this 20 is of type tensor, which is good. Just like his thing is of type array. Okay. So this is the same as the dot product of two vectors, but this is instead being done as matrices, which is exactly what we expected and it's what we wanted. But it's worth mentioning that NumPy does not have a dedicated method for performing matrix product. The dot product and matrix product are both implemented in a single method, np.dot. Okay, yeah, I guess it's, yeah. Similar for us, we don't actually have a standalone function for matrix multiplication. We just do a dot product with the transposed matrix. I think that's, we have a similar situation. I think so. Let's try things out. Hold on. Let's make this a 2x3 and this also a 2x3. And here, let's make sure that this actually works, even if it's an actual matrix with many rows and with multiple rows and multiple columns. So 3, 4, 5, 6. And then the raw B will be basically the same situation. 5, 6, 7. 2x3, 2x3, b.t. We're transposing it. Okay, let's run this. Let's see if this works. Let's make sure this works. Yeah, okay, so it's doing the correct matrix multiplication, 20, 38. So the 20 is from this row and this column, I guess. This thing gets turned into a column. This row and this column. The 38 is between this row and this column. The 47 is between this row and this column. And the 92 is between this row and this column. Dot producted, of course. So just like NumPy, the matrix multiplication is implemented in the np dot dot. We also have our t dot dot, which is the same implementation. Okay, now that we have gotten through matrix multiplication and we understand how it works, hopefully, let us implement this back into our exact example, and now we're going to have a batch of inputs instead of just one input. So let's come over here, and we're going to have raw inputs, colon equals a list of float 32, and we're going to start out with these values. This will be our first row, I guess. And here, instead of having this, we will have inputs, or rather raw inputs. Very good. And okay, now let's see. Let's go back into our inputs and weights. When converting them, we mentioned that we need to perform dot products on all the vectors that consist of both inputs and weights matrices. As we have just learned, that's the operation that matrix product performs. So we're going to have a matrix of inputs and a matrix of weights, and we're going to be doing the matrix multiplication. So yeah, that's exactly what we're doing. To turn the row vectors is currently consisting of into column vectors. Okay. Initially, we were able to perform the dot product on the inputs and weights without a transposition because the weights were a matrix, but the inputs were just a vector. So before, we were able to just do the dot product simply. We didn't have to transpose anything. But now we're going to be having inputs as a matrix and weights as a matrix, so we're going to have to transpose one of them. Because as you can see, remember what I told you, the inner values have to be the same in order for this to work. Because this guy's trying to do things with 4 values and the dot product with something of 3 values, and that's just not going to work. So one of these has to be transposed. If we transpose the second array, values of its shape will swap their positions. So if we transpose the weights, the 4 will go over here and the 3 will go over there. And then we'll have it set up properly, that there will be 2 3s outside and the 4s inside. So yeah, so he wants to transpose the weights. And then after transposition, we can perform the matrix product. If we look at this from the perspective of the inputs and weights, we need to perform the dot product of each input and each weight set in all their combinations. The dot product takes the row from the first array and the column from the second one, but currently the data in both arrays are row aligned. Transposing the second array shapes the data to be column aligned. The matrix product of inputs and transposed weights will result in a matrix containing all atomic dot products that we need to calculate. The resulting matrix consists of outputs of all neurons after operations performed on each input sample. So let's see. So let's break this down. So we have our initial weights, our initial inputs. So we have 1, 2, 3 batches, 3 sets of inputs. Then we have 1, 2, 3 neurons. Now you could have 4 inputs and 3 neurons. It doesn't matter. But in this case, we have 3 inputs and 3 neurons because there are 3 sets of weights and then there are also 3 biases. The outputs equals the dot product between the inputs and the weights that have been transposed. So we're transposing the weights so that these weights come over here, and then these weights come over here, and then these weights come over here. And then we're adding the biases. So let's take a look at just the dot product between the inputs and the transposed weights. We have 3 weights. I'm sorry, we have 4 weights, which means there are 4 weights because, okay, sorry, we have 3 neurons, which means what are we expecting? We are expecting 3 outputs for every input. So we have 1, 2, 3 inputs, so we're expecting 3 outputs for every input. That means 3 times plus 3 plus 3, or 3 times 3, so we're expecting 9 outputs, okay? And that's exactly what we get. We get 9 outputs. We get a matrix of a 3 by 3. This would be the first, I believe, this would be the first neurons, hold on. this is the first neuron's output for the first input. So this is the first neuron. So it's going to be this input times the first neuron's weights, which is going to be this output. And then we're going to take a look at still the first input times the second neuron's weights, and that's why we transpose the weights instead of the inputs, because we want it to be, we want all the, this is the first pass. Here are the outputs from the first inputs. And we get, and so they're row aligned, which is great. We want that. So these are the first outputs from the first inputs, and these are the second outputs from the second inputs, as opposed to what it would have been if we had transposed the inputs and left the weights untouched. We would have had this column. We would have had something very weird, actually. It would be really weird. It would be like a 4x4 thing. It would be weird. So this is how we do it. That's why we transpose the weights. So here we have the first input, the first neuron, and this is the first neuron's output for the first set of inputs, second neuron's output for the second set of inputs, third neuron's output for the third set of inputs. And that's our layer. So this is the layer's output from the first inputs. Here's the layer's output from the second inputs, following the same pattern. And here's the layer's output from the third inputs. Okay, so he's coded this up. Now it is our turn, I think. Yeah, let's do it for us. So what are his input values? Well, he has 1, 2, 3, and then 2.5. 1, 2, 3, 2.5, so we have that. And then he has 2.0, comma 5.0, comma -1.0, comma 2.0. And then he has -1.5, 2.7, 3.3, negative, I'm sorry, I already forgot it, -1.5. Nope, not -15, -1.5, 2.7, 3.3, and -0.8. So there you go. These are all the inputs. And then the weights should be the same as they were before, right? Yeah, so the raw weights are the same. We're passing it in with a shape of 3 by 4, because there are now 3 inputs. And then over here we want to do the dot product between, okay, so over here, after this, we want to do weights dot t to transpose the weights so that it would look like this instead. And then we want to do the dot product between these two things. And for now, I want to just print out dp to see if we get the same values that he got. So let's check this out. And also, we have to comment on bias for a second. Great. All right. Let's see. What do we got? Oh boy, these are not the right values at all. Okay, so something's wrong. Clearly. What's wrong? Have the right inputs. 1.1, 2, 3, 2.5, 2, 5, -1, 2, -1.5, 2.7, 3.3, -0.8. We're passing in with a shape of 3, 4, because it is of type of shape 1, 2, 3, 1, 2, 3, 4. Very good. Float 32, float 32. The weights 2, 8, -5, and 1. 0.0. Let's put that in. 0.5, -0.91, 0.26, and -0.5. Great. I wonder if he's doing this. I wonder if he is adding the biases here. Not sure. Hold on. We'll check that. We'll check that in a second. -0.26, 0.27. Yeah. Okay. Maybe it's possible that he's not just showing the dot product, but he's showing the final output, which is plus the biases. So we have to check that output. No, something's wrong. Oh, we have a weird shape, don't we? 1, 2, 3, 4 by 1, 2, 3, 4. That's weird. Should not be like that. That is weird. Hold on. Yeah, there's something really wrong with our dot product here. Ah, because we're passing in the weights first. We shouldn't be passing in the weights first. We should be passing in the inputs first. That was really stupid of me. Inputs, comma, weights. Yes, yes. dp, yeah, that's what we wanted. Okay, 2.80002. Yeah, we're getting the right values. There are a few issues because computers don't know how to do math, as I've said before. I wonder if we change these to float 64s, will we get like more precise values? I wonder. Let's change this also to a 64. Yeah, it's funny. We do. Well, for some of them we get more precise stuff. For others we don't. So let's just stick with the float 32 as it takes less memory. And we'll run with that. So, okay, good. So we have our system set up in Golang. So this is, yeah, it's funny how many more lines Golang takes than Python. I guess it's just because we're, like, in theory I can make this much less lines. I can make all of this just one line, but it would be a very weird line. Anyway, we mentioned that the second argument for np ... is going to be our transposed weights. Yeah, they mentioned that. I forgot to do that. So yeah, inputs first, then weights. So first we will be the inputs, but previously weights were the first parameter. So we did have weights as the first parameter. We changed that here. Before we were modeling a neuron output using a single sample of data, a vector. But now we're modeling a step forward when the model layer behavior is on a batch of data. So before we were doing it just with one sample, now we're doing it with a batch. We could retain the current parameter order, but as we'll soon learn, it's more useful to have a result consisting of a list of layer outputs per each sample than a list of neurons and their outputs sample-wise. In other words, the way we have it outputting is this is the outputs from the first layer with the first samples. This is the output from the layer with the first samples. This is the output from the layer with the second samples. And this is the output from the layer with the third samples. That's a lot better than having, this would be the first neuron's output for all of the samples, the second neuron's output for all of the samples, and the third neuron's output for all the samples. And so the layer outputs would be column-wise, which is not as good. We want it to be row-wise. That's good. We want the resulting array to be sample-related, not neuron-related, as we'll pass those samples further through the network, and the next layer will expect a batch of inputs. So essentially this will be the next layer's inputs. And we want this to have a very similar form we can use this as the next layer's inputs without transposing it. If we did it weights then inputs, we would have to transpose that and then pass it in. So this is better, essentially, because we could just throw this straight in as the next layer's inputs. Because again, the thing that we're modeling right now is the first layer, but imagine if we have a second layer over here, well, that second layer would be receiving this as its batch of inputs. Okay, we can code the solution using NumPy now. We can, we're using, okay, so I guess this is the end of the chapter, maybe? No. We can code this solution using NumPy now. We can perform the np ... on a plain Python list of lists, as NumPy will convert them into matrices internally. We are converting weights ourselves through the perform transposition operation first, which is .t, in the code, as plain Python list of lists do not support it. Speaking of biases, we do not need to make it a NumPy array for the same reason. NumPy is going to do that internally. So he's saying a lot of things related to NumPy specifically. This is not for us. We are going to have to make our biases into a tensor. Our program will not do it for us by itself. Okay, so now he's doing the exact same thing, except now he's adding the biases to the output, and then he's getting the final output. So let's do that as well. So output, let's just uncomment that, equals the dot product plus the biases. Print out output. And run it, and we get nil. Something's wrong. That's not good. Why is something wrong? Add. I guess possibly it's because here with shape. Sorry, it's t dot with shape. What is this supposed to be? 1, 3. Yeah, I think. No, something is still wrong. Okay, let's print out the error. fmt.println error. Let's see what's wrong. Add failed. Shape mix matched. Expected 1, 3. Got 3, 3. So it's complaining because the dot product is coming out with a shape of 3 by 3, and our thing is with a shape of 1 by 3. The biases, that is. So it's having trouble adding them together because it's not expecting that. But what I wanted to do is basically figure out that we want to add this to this, and then add the same thing to this, and then add the same thing to this. So I wonder how we can do that. Options. I'm assuming you could pass in like an option. T dot with reuse. With reuse passes in a tensor to be reused. Reuse. I don't know, I guess bias. Like we're telling it we want you to reuse bias for as many times as we need. Will this work? Add failed. No. Okay, so that's not how it's going to work. T dot. No, this is problematic. I didn't really expect this to be a problem, but then again, it's okay that it's a problem. When adding a sparse tensor to a dense tensor, the result of it is a tensor dense. What does that mean? Right, so this is showing that you could do the dot add thing between stuff that has the same shape, but we want to do stuff, even if it doesn't have the exact same shape, we want it to figure out that it should just reuse the second parameter that's passed in. This is problematic. Add performs element-wise addition. These operations are supported. If unsafe flag is passed, the data of the first tensor will be overwritten. If the unsafe flag is passed, and the data of the first tensor will be overwritten. No, I don't really care about that. With slices that are using patterns repeated enough, append, yeah. Our abstractions use manipulate. Okay, addition. No, well, that's not the word I'm looking for. I wonder if we could Google it. Golang. The problem is there's not really much documentation on this library. Tensor addition different shapes. Let's see. Yeah, there really isn't that much. Yeah, there's no documentation. We got to just sort of figure it out by ourselves. So let's see if we can figure it out. I wonder if I could just like try things. T dot. Bias. Dot. And performs T plus other element wise. Both T and other must have the same shape. Yeah, they have to have the same shape. That's really annoying. How do you do it if they have different shapes? There's got to be a way to do this. There's got to be a way to do this. I'm sure there's a way to do this. We just have to think of it. dp dot add. Wait, no. dp doesn't have a dot add thing? That's funny. Why does biases have an add? This is of type tensor. This is of type dense. That's weird. That's weird. T dot new with backing with shape. New with backing with shape. The above code will not go because the structure holds the underlying array of string. It is a dense. Currently, the tensor package supports a limited type of genericy limited to a tensor of any primitive type. This is a little bit concerning. Really? Yeah, it's just gonna throw an error. Mismatch, shape mismatch expected 1,3, got 3,3. That's weird. Bias. We want to add, let's put it this way, add the bias to DP. I wonder if this will change things. Expected 3,3, got 1,3. Okay, so it's saying, oh, I'm complaining the bias is a 1,3, but maybe now if we pass in t dot with reuse, and you can pass in bias. This is weird. With reuse passes in a tensor to be reused. That doesn't make any sense. Nah, it's still wrong. I don't even know what the t dot with reuse. Let's see. Options. I want like a list of options. Use defines BLAS implementation. Core Ginja should use the default native. These are the other options. Don't know what that means. Can be used with other construction options like with shape. Don't know what that means. With engine. Not sure what that means. In a 2D case, there are only 2 options. No, thank you. No, okay, nothing. Oop. I wanna not have to reshape it is the only thing. Let's see. Biases dot t dot wait, there's no reshape? Set shape? There's no like reshape set shape type thing? Yeah, tensor dot reshape. Yeah. Oh, but right, so bias is of type dense, right? Yeah. So hold on, biases. I wonder if we just var biases t dot tensor. I wonder if we just turn it into a tensor. Could we then do it? Will it then figure out to do it? I don't know. Maybe. Let's see. Add failed. No. Okay. Okay, fine. So now. No, biases. Bias is. No. Yeah, biases. Biases. Should be biases. Dot reshape. How do you reshape? Okay. And then if I just pass in a 3,3. This will probably just error out, right? This will probably just error out. T.println. I wonder. Let's see. It's probably just going to error out. Cannot reshape 1, 3 into 3, 3. Yeah, I thought not. Okay. That was a shot in the dark. This is problematic. I did not realize that this was going to be a problem. Did not realize that this was going to be a problem. A simple and concept, however, let's start with something more familiar. This is a visual representation of a slice and go. No, I don't need that. Thank you, thank you, thank you. Yeah, thank you. You didn't get inspired by NumPy enough, apparently. Copy. Don't use pool. I wonder what that is. Don't use pool. Make sure the functions don't use the tensor pool provided. No, I'm good. ITOL is the index to location. No, make reduce, mask reduce applies a reduction function of type mask reduce event to mask and returns either an int. No, we don't need that. I'm literally just going to go through the entire thing and see if there's something. Range, register, request equal, registers a data type can be compared for a call. No. Register float, register number, register order, return bools, return ends, return tensor. What is this? Return tensor returns a tensor to their respective pools. I'm not even sure what that means. Sample index, slice details, sort index, sum ints, sums a slice of ints. That's nice. To mat, don't know what that means. Transpose index, returns the new index given the old index, okay. Unsafe permute, and untranspose index, use pool, AP, what's this? An AP is an access pattern. It tells the various ND arrays how to access their data through the use of struct. Okay, fine. Make AP. Make AP creates an AP given the shape ends, right? Yeah, I don't need anything from the AP. I don't think so, at least. Adder's an interface. It has 2 functions. Oh boy. This is where we were. Okay. It has 2 functions. This is one that we're trying to use. Add scalar adds a scalar to the tensor. Left tensor indicates if the tensor is the left operand, whether or not the input tensor is a clobbered is left of the implementation. No, I don't really need this. Argumenter, BLAS, which BLAS, bitmap, new bitmap, clear, is set, boolable, by CS, no, new CSC. This is how it goes, dudes. You gotta just do it this way. Clone, data order, data size, dense, creates a dense tensor from a compressed one. Dims, dtype, engine, format, get, go into code. None of these even have documentation. Reshape, scalar value. These are just different types. I don't need this. I need, yeah, we've already gone through all their functions, I guess. Huh. I guess there is no way to do this, which is kind of crazy. Wonder how we're gonna figure this out. Like, we're gonna have to come up with our own solution, our own function, I guess. Yeah, let's just, okay, fine. So let's code this. Let's do this. I was assuming we were gonna have to do some stuff by ourselves. So let's do it. New file. Useful funcs dot go. I don't even know if this is how we would do it. I'm just gonna do an underscore useful funcs dot go. Package. Should we make this into its own library? No. Package main. I don't even know. Okay. Func. Add. No. Bias. Add bias is. And this will take in the, I don't know, inputs, which will be of type t.tensor. And we also have to import tensor. Import, yes. And it will also take in biases. Yeah. Yeah, t.tensor. Okay. Okay. Now, in fact, we don't even need this right here. Okay. Biases will always have a shape of like 1 comma something, right? That should always be how biases are. There's no need to have like multiple dimensions. So right, so here, new shape colon equals inputs dot shape. Yeah, this is really weird. Biases 10. New biases colon equals t dot new with shape new shape. What's wrong here? Cannot use new shape variable of type tensor.shape as int value and arguments to t dot with shape. Right, so we just have to expand that, I guess. Yeah. NB for just new biases colon equals. How many dimensions would this have to be? Well, we need to know the shape of this thing, which is going to be a matrix. So yeah, it's going to be a 2 by 2 thing. Float 32. Okay, so hold on. Yeah, so I haven't been explaining what we're doing here. I'm trying to figure out a nice coding way to basically just make it so that what we have is we have biases set up as just a basically one-dimensional row vector essentially. So it's a 1 by 3, but I'm trying to make it so that we can just code something that will dynamically take this essentially. It will take in this, and it will also figure out the shape that it needs to be, and it will basically just turn it into. In our case, it's going to turn it into like this, because it needs to be a 3 by 3. So, but it needs to do this dynamically. So I'm getting the shape that it needs to turn into, which is based off of the inputs, and then I'm going to make the new biases a situation that will be like NB here, yeah, we're gonna make a new slice. So this is gonna be like the new biases format. It's gonna make like a new two-dimensional slice situation, and it will have the size of inputs dot new shape index 0, and then for I colon equals range of NB, right, hold on, so yeah, we need to also get the original bias values. So for I colon equals range of NB, we need to get the original bias values, and we need to put that into this array somehow, into this slice somehow, and we need to do it several times. So that's going to come into the for loop. But the original bias values, how do I get like the original bias values? I guess I could do like biases.asSlice. Biases.slice. Yeah, this will return like the slice version of biases. I assume. No, I guess not. I guess not. How would I get it like as a slice? This is going to be a long. This is going to be a very process-intensive function. I don't like this. I want to find a better. I want to find a way to do this. I want to find a way to do this without making our own function a little bit. Here. This is the kind of challenge that I knew we were going to have turning things into Golang, and this is the fun part. We have to just sort of figure out this problem that we cannot add it because the shapes are not aligned. I'm honestly shocked that there isn't like a built-in function. Biases dot. What does apply do? I wonder what apply does. What does this even do? Apply takes in. Yeah, I'm not even sure what that does. Biases dot, not clone. Oh, wait, this might help. This might help. The clone function might help. Yeah, okay. The clone might help. Clone would help, I think, maybe. NB index I equals like make, but of shape like new shape index 1, and then NB index I equals biases dot clone Hello. Hello, we seem to have disconnected, and we're back, apparently. But... okay, let me find out where we left off. Okay, fine, so that's where we left off. That's fine, we haven't really done anything. The problem is we have to just paste biases, and we have to like put the values of biases into every row in our new biases matrix. So I'm trying to figure out how to do that. So we're basically just getting the slice version of biases now, because it's returning two things, and then we're setting it to S. But it's not working because you cannot use S variable type tensor.view as float value in assignment. So yeah, so that's not going to work. I have to find a way to get like the raw bias values. To put it in our thing. To put it into our new situation. Here. I'm sure that they have something like that. I think it's even at the top of the thing. Yeah, it should be like in a table up here, right? T.slice ... That's what I want. T.slice ... What's wrong? Expected operate found ... Well, that's what it's telling me to do. What do you want? You want a ... of T.slice. This is the syntax that it's telling me to use. Let's just here. Let's just try stuff out for a second. Let's try stuff out with our DP, with our dot product. So fmt.println dp.slice. Let's see. Nope. Okay. New biases declared but not used. Okay. Everything in here are comments, please, and you could get deleted. Except for package main, I guess. Yeah. Okay. Expected expression. Yeah, I'm not sure what the dot slice thing does. It says that it should just give me everything. Like this is how it works for. How do you turn it into a slice? Is something I'm interested in. Dims, type, reshape, strides. No. Is there any way to do it? No, there isn't really a way to do it. Yeah, there isn't really a way to do it. Yeah, there really isn't a way to do it. That's really annoying. Okay. Huh. This is quite a pickle. How long have we been spending on this one problem? I don't even know. I mean, I could think of a way to make that function, but it's going to be a disgusting function, and it's going to be like a long function. It'll have like no speed. We want this to be a nice, quick way to do things. I need like just to be able to add things. And I need you to like handle it dynamically, I suppose. It can't do that. Reuse must be a dense because the result will always be a dense. Not sure what this even means. converting a sparse tensor to a dense tensor. The result is of, I'm not sure what that is. And the result is of tensor.tensor. And this is the matrix. Vice versa. Also, it is going to be a tensor.dense. Sample. Documentation. Tensor new, tensor with shape, tensor with backing, long struct. I'm not even sure what a long struct is. T dot slice nil comma s parentheses 1 s is the type that implements tensor dot slice. Not sure what that is. Sum sliced. T is a new thing with backing. Here's the backing, 4x4. S colon equals a new slice. T dot S colon equals T dot slice. Not sure what this is. 1, 2, 3, 4. I'm not sure what's going on here. Func. Borrow bool, don't use pool, inner. Mask reduce, mask instrument. Random range, register number, return bool, slice, sum. Types. Why does the adder not have what does the add scalar do? Is add scalar what we're looking for? I doubt it, but let's just see. T dot add. No. Okay. I think that I'm at the end of my line here, and I'm going to do something very not nice, which is look for a different package. Tensor. So this is what we have been using. Packaging tensor provides basic set of tensor data structures and dimensional arrays of data based on APAC arrow go /tensor and intercompatible with those structures. Let's see this one. Here it has a bunch of ints. Bool to float, copy. No, I don't really think that this is gonna be what we're looking for, I'll be honest with you. Add. Has like a bunch of different types. No. The fact that I'm looping through the dates that it was added is really annoying. Okay. Hold on. Wait a minute. I accidentally just left the stream place. We still going? We're still good? I think we're still good. Okay. Hold on. Yeah, we're still good. Wow, okay. Oh my god. This is really annoying. Tensor. Okay, package. Tensor is a package that provides efficient, generic, and dimensional arrays and go. Let's see what you got. Example, basics. Let's see. Create a 2x2 matrix of integers a equals new. Wait, is this not exactly what we've been using? Maybe, I don't know. This is exactly the same syntax. Accessing data, yeah. Yep, this is exactly what we've been using. Okay, let's see how you add things, I guess. This is exactly the same package. Yeah. Create a 2x3. Reuse data order with reuse. Wait, what's this? T0, T1, T2, 0, 3. So these two are adding. T0, T1, T2. No, but I need an example of addition. Where the shapes are not the same. What is this with reuse? Reuse equals new with shape. What is this? What is the with reuse thing? Is that exactly what we're looking for? Operations involving sparse tensors also do take the usual function operations. Like, I have to edit this. That's weird. I really feel like the with reuse option is what we're looking for here. No, because it won't even get past the first step. It needs to have the same shape for no reason. I have no idea how to do this. I'm actually at a loss. Yeah, NumPy really is amazing. That is definitely true. T dot dot inputs weights returns a multi-dimensional thing. If there was a way to like iterate through all the outputs, all the dot products. dp dot There should be like an add to all or something, like add to all, or like there should be a way to add to every index or every dimension a certain like there has to be a way to program this. And wait, no, this is the wrong thing even. I want to change things. I want to add to something. I want to add to every element in DP. So weird that you can't do a dot add for tensors. That's weird. That's weird. What's this? What does apply do? Not sure. So unfortunate. This is so unfortunate that we have this incredible library, and it is an incredible library, and it's just missing this one functionality that we need. I'm having trouble figuring out how to seamlessly make a function to do this for us. I need to make the backing somehow. And the more I think about it, the more I just come back to this fact that we need to figure out how to make this function. This is the only way to do it. And we need to come up with, because the challenge I'm having is creating this backing in a seamless way, in a nice, easy way. Equals make, and then I guess we just have to do a double loop for j. Like, I knew I could have done this at the beginning, but I wanted to find another option, and I guess I didn't. So I guess we're making the function for j colon equals range of nb index I, nb index I index j equals biases dot at, and I guess I just need to pass in a j here. What's wrong here? Oh. What's wrong now? Cannot use biases. Type of value. Interface is float32. Need type assertion. Can't just like transform it. No. Oh my god. Val underscore colon equals this. Thank you. And then this going to equal a float32 of val. Can I do this? Undeclared name float32. Float32 of val. Nope, cannot convert val variable type interface to float32. Need type assertion. cannot get a normal I think I searched this up in another video. Convert interface to float Golang. Yeah, what a mess. What a mess. Okay, you know what? We're just going to keep our biases as a float 32. And we'll pass it in as a float 32. Oh, and inputs needs to be a t.tensor. And then over here, we can just do copy to nb index I, everything from biases. Okay, and then new bias is that with a shape, and then t dot with backing, biases. Nope, the new biases, the nb. And then we want to return new biases. I guess this thing's going to return a t.dense. Or like, what's the syntax, right? Like this? No. Like this? Yes. Okay, so this is a good function. The function's going to take in, I guess, actually, you know what? We should just do like shape. And then this will be of type like that with int 32 or something. And then this could be just, we don't even need a new shape value. And then this will be just shape 0 and shape 1. And then over here we could just do shape colon, no. How do you expand how do you expand to get just open it up? Is there even a way to do that in Golang? No. I forgot the syntax. So okay, hold on, let's put this over here. No, we need that. I guess we know that it will only be a two-dimensional thing. It's not new shape, it's just shape. Shape. What's wrong here? Cannot use shape variable type as. How about if we just make this an int? Okay, there you go, that works. Okay, excellent. And then we return new biases. Okay, so this should work. So it takes in a shape, it takes in the biases, and then it creates like this new bias, which is going to be a multi-dimensional thing, which will be the type of shape, and then it will return the new biases as our new thing, and we can move on. And in fact, you know what? No, I don't even want it to do it like this. I don't want it to return. I don't necessarily want it to return anything. What we can do is we can just program it all inside like that. Oh, that's why I had passed in the inputs. Oh, I'm such an idiot. Okay. Let's back this whole thing up till we have our inputs. Excellent. Okay, so now that we have our inputs, and right, so we have our inputs, we have the bias array, the bias tensor thing, the bias tensor object struct or whatever. Now we could add the two of them, and we could simply say, yeah, this is going to do, okay, so t.add the inputs inputs and the biases, the new biases. And yeah, that will return a tensor and an error, so we can just return this, and so our thing will return a t.tensor and a error. How do you return an error? I forget how to return it. Right, this needs to be a star. No? What do you return? You return a t.tensor and an error. T.tensor and an error. What's wrong? Oh, it needs to be in parentheses, I think. Yeah, there we go. Okay, so this is going to be our function to add biases. Excellent. And now our biases will instead be just a straight up list. What's wrong here? Oh. It's funny though, because I don't even think that this kind of code is going to be very long used. We're going to turn this into like object-oriented stuff. So anyway, here, output, comma, parenthesis, underscore colon equals, add biases, and the inputs are going to be dp, and the biases are going to be biases. And this should work, honestly. Output. Error. Okay. Sanity check failed. Shape mismatch. Expected 3 by 3 got 3. That's interesting. Where did this happen? On line 32 in main. On line 15 in useful functions. Okay, so when we were trying to make the thing, when we were trying to make it into a tensor, we got an error. I wonder why. Oh, because the new thing, the new, yeah, the new bias shouldn't be multidimensional. We went through this in the last video. It should just be one-dimensional. So we have to, because if this is going to be the backing, it needs to be one-dimensional. So it needs to be new shape at 0 times new shape at 1. And then what we can do is we can say for I colon equals range of NB. NB index I equals biases indexed I modulus the length of biases, I think. This should work. What will this do? This is going to populate our NB. So let's say biases is 1, 2, 3. So this should populate NB as 1, 2, 3, 1, 2, 3, 1, 2, 3, however many times it needs to do that. And I believe it should be length of biases. So that when the I gets to reach the length of biases, it just goes back to 0. And then 1, 2, 0, and then so on and so forth. So I believe this should work. Okay, yeah, this worked. I think. Yeah, 8.9, -1.8, 0.2. Okay, let me explain what we just did, because oh my god, did that take a long time. And all of this will probably be saved for anyone that wants to check in. There'll be a timestamp from like when we started this issue until until now, so that you could skip all of this. And okay, and now we have the function made, and so basically let me refresh our memory as to the issue. The problem was we couldn't add the biases to the dot product with the normal t.add function. Why? Because the t.add function expected them to have the same shape, and they didn't have the same shape. They had totally different shapes. The biases had a shape of 1, 3, and the DP had a shape of 3, 3. So they didn't have totally different shapes. They had a similar second dimension, but the first dimension was off. So instead of, well, not instead, I looked for a function or some way to do it within the tensor package, but I couldn't find anything. So what I did was I turned biases back into just a one-dimensional normal Golang slice. And then I made this new function called add biases. And you're passing in the DP and the biases. So what does add biases do? Well, let's say the biases, let's bring everything over. So biases is a float like this. In our specific case, like add biases, thankfully I made it so that's dynamic, so we'll be able to use it later if we need to. But the biases looked like this, and the DP looked something like, not exactly like, but it looked something like, oh boy, looked something like this. Hold on. There is a way. No, there's no multi-line comment. Yeah, there's multi-line comment. Excellent. It looked something like this. Let's say 1, 2, 3, 1, 2, 3, and it was like a multi-dimensional thing. 1, 2, 3. This is a good way to visualize it. And so each one of these is its own thing. It was a 3x3 situation, right? Okay. Right. Great. Okay, so DP looks something like this, and the biases look something like this. We had to figure out a way to make biases look like, have this, basically we had to figure out a way to make biases have a shape that was whatever DP's shape was, which is in this case a 3x3. So we had to look at biases, and we had to like copy this and do, okay, so that's 1, 2, 3. So that's basically what our function is going to do. And so this is the function. So first of all, the function gets the new shape that biases need to have. And basically, biases need to have the inputs.shape. They need to have the shape of inputs.shape. Then we need to make our new backing. So here, I'll call this new backing. And the new backing, is going to be our new backing to our new bias tensor. That will look like, I deleted it, but it's gonna look like this. This will be our new bias tensor. And so if this is going to be the new bias tensor, then the bias backing, the new backing, is going to have to look like this. Something like this. Hold on, stop it, please. It's going to have to look something like this. Just a straight up one-dimensional situation, but it's going to have to go 1, 2, 3 times, right? And this is what the new backing is going to look like, because it's going to have this, and then it will have that again, and then that again, and then we're going to add this, or rather, we're going to add this to this, and then this to this, and then this to this with our t.add method. So how are we going to do this? Well, we set up new backing to be a one-dimensional float with the shape. What's the shape going to be? Well, it's going to be the new shape index 0 times the new shape index 1, right? Because the DP is a two-dimensional thing, and so the shape index 0 is 1, 2, 3, and the shape index 1 is 1, 2, and the shape index 1 is 1, 2, 3. So it needs to have a length of 9. So it's going to be a new slice with a length of 9 in our particular case, but this is more dynamic. And by the way, yeah, we need to have some like comments here, like inputs must be 2 by 2. And stuff like biases must, the length of biases must be the biases, okay, here, length of biases must equal inputs dot shape index 1. Basically, that's what it has to be. The length of the biases has to be, yeah, 3. So the length of the biases also has to be 3 so that we could duplicate it. So once we have our new backings set up, the building blocks of it, now we can start populating it with the proper values. And so that's exactly what we do in this step. For I colon equals the range of new backing, let's loop through every value in new backing and set it to the appropriate thing. What is the appropriate thing? Well, new backing index I equals biases index I modulus the length of biases. What does this mean? Well, when I is 0, new backing will be, when I is 0, new backing index 0 will be biases index 0. And so that's 2. And then when I is 1, it will be 3. When I is 2, it will be 0.5. When I is 3, when I is equal to 3, now we have a problem because we don't have anything left in the biases. So we modulus the length of the biases that when it's, well, the length of the biases is 3. So when I is 3 in our case, I will jump back to being 0, and then it will be a 2. And so that 2 is going to happen over here. And now I is no longer 3 anymore. Now I is 4 because we're looking at like the new backing index 4. And so since it's new backing index 4, well so the index it's going to get from the biases will be 4 modulus 3, which is 1. And so we'll take the 1th element in biases and put that into index 4. And so that's how we populate the new backing. And if you don't understand that review modulus operator and how it's used to like loop through things and jump back over and go through a loop like that. And so there you go. So now we populate the new backing. Now we make our new tensor with the appropriate shape, the new shape, ... like the expanded shape, with the backing of new backing. And that's its new, and so now we have the appropriate bias configuration, and then we return t.add inputs comma new biases, and so now we can use that as a function, add biases to add our biases to our dot product, and there you go, and we could print out the output, and it works, which is excellent. So there you go. I knew we were going to have to make some functions along the way. I guess the first time we had to do it, I was just a little bit resistant, but we did it. It worked, and excellent, good stuff, I suppose. Sorry that that took so long. How long have we been going is the question, because that took a long time. Okay, we've only been going for an hour and a half, which is less than I thought. But anyway, there'll be a marker in the video to just jump straight to the end of my exploratory phase. And you can see the results. Okay, moving on, I suppose. Now we can implement what we have into code. So he gets the results. This is his code. Here's his inputs. We have our inputs. By the way, yeah, so I don't even know. In the explanation, sorry, oh my god, I messed it up because like everything is in the thing. I made a new file called usefulfunctions.go. This is where we're going to put all the functions that we're going to need to make ourselves, at least in chapter 2. Maybe in future chapters we'll have to expand this a little bit. But for now, this is how it goes. This is how it goes. For now, this is the format that we have. Simply a page for useful functions. If we need to expand this later, then we will. And so the add biases function goes into the useful function folder. File, not folder. And this is all in chapter 2. Okay, great. So now that we have the added biases, we could print that out. We print out the outputs. We get the appropriate values, which means that we did everything correctly, I believe. Yeah, very good. And we can move on. As you can see, our neural network takes in a group of samples, inputs, and outputs a group of predictions. So yeah, so this is what our neural network is doing. Our single layer neural network. It's taking in the inputs that here's our raw inputs that we turn into a tensor, just like him. He has his inputs, and he automatically gets to turn it into a numpy array. We have to do that by hand. Here's our raw weights. We turn that into a tensor. In fact, this is weird over here. We don't really need this syntax. We could just have a colon equal, I think. Yeah. And then so that's his weights. This is our weights. He transposes his weights over here. We do it immediately. Biases for him is just like biases for us. It's a simple slice, which we then turn into a proper tensor in the add biases function that we made. And there you go, and it prints out all the appropriate values. That's weird. I don't know why this thing's down here. But anyway, it works, which is amazing. And that is the end of chapter 2. Okay, what a day. Any questions, comments, concerns, please comment it down. I know that this video was a little bit chaotic and whatever, but I hope it worked out in one way or another for you. Sorry for that big chunk, like maybe it was even an hour in the middle where just we weren't really doing anything. Okay, great. So that's the end of chapter 2, where we've now turned everything into the tensor way of doing things, and we focused on, so we learned in chapter 2 about tensors, what they are, how to use them. We learned how to code them in Go, whereas he's doing it in NumPy. We learned about batches of inputs instead of just one thing of input, which that was like the killer. So batches of inputs where we're turning in many inputs. Again, any comments, questions, concerns, leave a comment. I will definitely respond 100%. Apologies for the chaoticness of the episode, and good luck coding.